name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to the 14th ITS RF Measurement Seminar. Today's seminar is Resolving RF Interference, and we'll talk about resolving co-channel interference in particular today. This particular talk is the first of three that I'm going to do on resolving interference problems, and in these three talks I'm going to emphasize that we take an approach to resolving interference which is quantifiable and methodical. So instead of guessing what we think the problem is, I will present an approach and a methodology that I think can be used to methodically work out the source of interference, methodically identify the level at which that interference is affecting a receiver, and then work out in a methodical way some solution to the interference problem depending upon what those answers are. This is possibly in contrast to some other methods of resolving interference that I think are a lot more hit and miss, more helter-skelter. So, the way that we'll work through this is to first of all mention the three major types of RF interference. And the first, which we'll talk about today, is so-called co-channel interference. And this is interference, which I'll describe a little more in a moment, but basically this is interference where energy from some transmitter or some source is occurring on the desired frequency of a receiver that's experiencing interference problems. The second major type of interference is RF, front-end overload. And this is interference which is putting energy into a receiver at a frequency which is different from the frequency that the receiver is actually utilizing for its desired communication link or its desired channel. And on the face of it, you might think that if the interference is not coming in on the receiver's desired frequency, that you wouldn't see effects of interference, but in fact you can if you hit a sufficiently high level to cause the amplifier at the front end of the receiver to experience an overload effect. And then third, we have a kind of a miscellaneous, or I'll call it a zoo category, which will still involve interference either being on the receiver channel or not being on the receiver channel, but which does not arise as a result of a interference coupling mechanism that's commonly seen. So basically these will be the three talks, and as I said, in this talk we're going to be discussing co-channel interference.
What about adjacent channel?
And thanks for mentioning that. Adjacent channel interference, which can result in either RF front-end overload or can result in co-channel because of essentially a bleed over effect.
Into two categories.
Exactly, but I'd still put it into two categories. Well, as a matter of fact, I'll go ahead and draw the diagram out basically for how this could work. What we envision here are two parallel situations or conditions, and in the two conditions, we'll say that this is this is a diagram of what happens with co-channel, and this is a diagram of what happens with RF front-end overload. All right. Here's what we have. In both cases, we have a receiver which has a window in the frequency domain which looks something like this. And this is the desired frequency of this receiver. The F0 of the receiver, like so. We'll draw the same thing over here. Here's our receiver, and again, the center frequency of the receiver. And the receiver has some bandwidth associated with its desired mode of operation, bandwidth of the receiver, like so. And either we have interference energy getting into the receiver. Oh, in fact, I'll back up. Here's the receiver's internal noise floor down here, like so. And if this is a communication receiver, then it's picking up a signal that has some desired signal-to-noise ratio or some desired carrier-to-noise ratio. So we'll draw the receiver's desired signal inside its bandwidth as looking something like this. Here's its desired signal, and it's got some particular carrier level relative to its noise level. So we have some particular C to N level that's desired. And again, we have this in both cases. Here it is operating inside its desired bandwidth. Here's the carrier level, here's its noise level, and we have some desired carrier to noise level at which this receiver is actually operating. Now, we now get some kind of RF interference in. And this RF interference, if it's co-channel, all I mean is that the interference is getting into the receiver at some level, which might look like that. There's the interference power. And this power level of this interference is sufficiently high that the performance of this receiver is somehow degraded. And what's going on outside this receiver bandwidth is somewhat of a question mark. Here are some things that could be going on. It could be that we're seeing some sort of bleed over from some transmitter over here, which has a spectrum that looks like that. And this is the part of that spectrum that's getting in here. It could be that we have some communication system where we in fact have a signal adjacent to this particular channel, and this signal comes up and occupies some bandwidth like that. But for whatever reason, again, we're getting some kind of bleed over here. This would be the adjacent channel case, and say it looks like that.
Yeah, which other was a mask.
Exactly, and we'll talk a little more about masks later. But this is a case where if this thing rolled off like that, we might not have the interference problem occurring. Because we'd only be getting that much energy in there. But if it rolls out like that and we have all that energy, we've got a problem. Same thing with the putative emitter that I put over here going through like that. If this emitter had to meet an emission mask which brought its emission level down like that, then again we could avoid this co-channel problem. But the point here is that the interference energy is in fact somehow actually coupling in here. Now, there's another way that this can occur, and it's not due directly to the operation of a particular transmitter, but rather due to the operation of two transmitters. A case where we have a transmitter running on a frequency F1 here, and another transmitter running on some other frequency F2, which we'll draw here, looking like this, frequency F2. And then we get an intermodulation product where the frequency of the intermodulation product is equal to the sum and the difference of F1 and F2. The interesting thing in that case being that although this intermodulation energy can occur on this channel, neither of these transmitters is itself creating energy in its sidebands or its unwanted emissions that are actually on that frequency, but the operation of these two together can do this. And we can also get this kind of problem, well, I'll leave it at that for the moment. We can also have a problem with what's called a rusty bolt effect, where an emitter is running at some frequency, which we'll label F1, and where this produces emissions on other frequencies, which are 2 times F1 and 3 times F1 and so forth on up. And if one of those products from this rusty bolt effect occurs in that frequency, then again we're getting co-channel interference. We'll talk more about the rusty bolt effect later, and we've got a case history on that. Now, that's what, of course, we'll be talking about today. What we'll talk about for the second talk on RF front-end overload is a case where an emitter is putting out energy over here on some particular frequency, and no measurable energy at all is being produced over here on the frequency of the receiver that is having a problem, but due to the behavior of the RF front end of this receiver, this energy at the desired frequency of the transmitter that's causing the problem, in fact, will cause this system to degrade in performance. Specifically, it'll cause this noise floor to actually drop like that, like so, and it's not actually the noise here that's going down, it's actually the gain of the front-end amplifier, and that is a whole separate problem, which, as I say, we'll take up in the second talk next time. That's just a preview. And then we have, as I said, a sort of a zoo category. Now, one of the things that I wanted to mention or diagram out is, in fact, how NTIA and ITS in particular get pulled into looking at RF interference problems. Here, I'll draw a little box for the ITS organization, and here we'll show the places where interference reports get generated. Interference reports. Interference reports may be generated from the FCC. They may be generated via various government agencies other than the FCC, such as the Department of Defense, the Department of Transportation, Homeland Security, etc. And typically, but not absolutely always, reports from various government agencies or from the FCC regarding interference will come to the Office of Spectrum Management, NTIA, in Washington, and OSM in turn may route those reports to ITS, and ITS in turn may work with OSM to perform an investigation of the interference problem. Now, we only become involved, we being OSM and ITS, if at least one of the radios suspected, and I emphasize the word suspected of being involved in the problem is a federal government, is a federal system, a federal government system. So if either the transmitter that seems to be producing the problem or the receiver that seems to be getting the problem, or both, belong to the federal government, then, depending upon the reports that come in from the FCC or from various government agencies, typically, as I say, to OSM and then to ITS, then, if that condition is met, then we may perform an actual investigation, which typically involves basically, first of all, phone calls, then coordination, then measurements. I'll draw it like this: phone calls, coordination, measurements, and lastly, analysis and some kind of a final report, preferably an NTIA technical memo or an NTIA technical report if possible. Like so. Analysis and then finally this. Now, the other magic part of this particular equation is where the funding comes from. The funding, the dollars, can either come directly from a U.S. government agency that puts together an other agency agreement, an OA agreement, directly with ITS/OSM, or the funding may come from our S&E funds, or the funding could come via the Office of Spectrum Management itself, via basically the spectrum fees, which I'll draw here, via the spectrum fees that the federal agencies pay to NTIA on a yearly basis. So an agency can contract directly with ITS and or OSM to do the work, or they can provide the money via spectrum fees to OSM, and then OSM in turn provides that money up here for the investigation. Or, depending upon the situation, we can use the money that comes directly to ITS from Congress, the so-called S&E money that we have. And obviously, if there's no funding, then we can't investigate it. But that's the basic idea behind, first of all, getting the interference reports, and second of all, getting the funding together. So, suppose that we've gotten this far. The FCC and or government agencies have reported to OSM and then over to ITS that they believe that some radios that are federal government radios are either getting interference or are producing interference or both. And that a decision has been made jointly between OSM and ITS to undertake an investigation, and that we've got the money put together for it. That brings us right up to this point right here, and now we're ready for the next stage in the process. I'll wrap all this up as stage 1. So now we're ready for stage 2. Phone calls. This is something that I at least have gotten involved with many times in the past, and at this point I'll in fact go to the next board here. Important tip, always erase both boards before you do your talk. Take care of that, like so. Here we go. Now, when we or I call someone, I typically try to call, and of course this could involve emails as well. I typically try to call whoever is directly aware of and can describe the problem. This is important to do because oftentimes, here's what happens. Here's a radio system being operated, and this system develops some kind of problem. Some kind of problem arises. And you would think that there would be an internal problem-solving process to try to determine within the radio system what might be wrong. And sometimes there is, but sometimes there isn't. And sometimes people assume or jump to the conclusion that they're getting interference when in fact radio interference is not necessarily their problem. So what can happen is that a report of interference may be generated down at this level, which is a fairly low level in an organization. This will go to the next level of supervisor, next level of supervision, and then the next level after that, and so forth, until finally it gets to the Interagency Radio Advisory Committee representative for the department, if this is a federal system, for the department, say the Department of Defense or whatever, where this radio system is operating, and then this is the report that gets to OSM. Now, there are a lot of opportunities along the way for this original problem, as understood at this level, to get somewhat garbled. And this isn't because people aren't doing their work, but if you keep relating a story back and forth, things can get a little confused along the way. This can go from a maybe down here, a maybe, as in we're not sure what's happening, to a definite by the time you get to this point. We're sure that we're getting some kind of interference. My goal when I'm talking to people is to get down directly, get down to that level and talk to this person or these people right here directly and start asking them questions. It's important to get down to that level. I would recommend that no one who's investigating a problem ever just assume that by the time they get something that's gotten to the department level that they're getting the same story as you'd see down here. I'm not casting any aspersions on anyone through the process. It's just that this is impossible to keep a story completely straight all the way through. So, my observation has been that if you make about 2 to 3 phone calls or emails, you should be able to get down to that working level. If you haven't gotten to the working level in 3 calls, something's gone wrong. You're off track somewhere. So, once you do get down to that working level, what do you need to do? Well, you need to talk to them, and this is why I actually prefer talking to people over emails. What you're going to have to do at this point is work a little like a doctor or a diagnostician who's interviewing a patient to try to find out what's really going on here. And I will add at this point that approximately, I would say based on our experience here, approximately half of all interference reports are, or turn out to be, not radio frequency interference, but rather are coming from some other point of origination, just roughly. And if you ask a good set of questions here, you may be able to isolate it down as to whether it really is or is not an RF interference problem before you go out and do a lot of expensive field measurements and analysis. So questions are very much along the lines of, first of all, obviously, what system is affected? And you're going to want to get its technical parameters, which means you're going to want to get its operating frequency, its bandwidth, the modulation it uses, if it's a communication link. You're going to want to get its location. You're going to want to get its antenna characteristics. That's very important, etc. Get as much of that as you can. Try to get it directly from the operator. Again, reference books and sources like the government master file may not really contain the right information for the system. Try to get it directly from the system operator. Second, are there multiple locations being affected? Question 3, how often does it occur? Does it occur on a schedule? Is it predictable? This also has implications for how we'll go out to try to find the source of the interference later, if we think it is interference. Now, when did it start? When did the interference begin? Now, and I'll put it in quote. We should put that in quotes because we're not sure yet that this is radio interference. This is the tricky one because what can happen is you'll ask when did this start, and they will say, well, we think we first became aware of it in March. You say, well, what do you mean you first think you became aware of it in March? Well, and this is where you have to probe a little bit and be a little bit subtle. What you'll start hearing are things like, well, it might have been happening before March, but we had a different operator then, and he was working for a tech sergeant, and that sergeant said it wasn't a problem. But then we got a new sergeant, and the sergeant said it was a problem, and that new sergeant came on in March. Oh, so the interference didn't start in March. Okay, when did they first see this problem when the first sergeant thought it wasn't actually a problem? Well, that's been going on for a couple years now. Okay, now we know something more than, because otherwise we would have been looking for something that started happening in March. Now we know that actually the problem's been going on for a long time. Someone just finally decided that this was a problem. We also had a problem years ago where a system transitioned from analog to digital. These were point-to-point microwave links sending telephone calls. That's not done much now, but years ago it was. And what had happened was when the analog point-to-point links were running between various locations, they were getting interference from various radar systems. But on an analog link, people just heard a little bzzz, bzzz every so often, and nobody thought anything of it. Later, they converted to a digital link. The digital link provided a dump of bit error rate on the link as a function of time 24 hours a day, 7 days a week. And then they began to see that the bit error rate was jumping every 10 or 15 or 20 seconds. And they said, that's unacceptable. We need to do something about this. So here again, if you question them naively, they'd say, oh, the problem started when we first installed the digital links. And then you find out, no, the problem's been going on for many, many years, but nobody thought it was a problem with an analog link. So again, we're not going to look in that case for a transmitter that came on the air or came into operation when the digital link came in. We're going to be looking for something that's been there a lot longer. So this is a tricky question to ask, but you need to ask it well. The other questions to ask are, in effect, how does the problem manifest itself? How does it manifest itself? And I'm going to write etc. here because at this point, by the time you've asked these questions, hopefully you're basically working yourself down a mental tree that says that I'm going to try to home in on what might be going on here, based upon whether it comes up all the time or whether it's a very intermittent problem, based on whether they're seeing it one place or they're seeing it lots of places. For example, we've had interference to Earth station links, bringing signals down from satellites, which were occurring entirely in coastal locations in the continental United States, Hawaii, and Japan, but never occurred more than a few miles away from the coast. What might that mean? Maybe it's coming from ships offshore, because for some reason it occurs in California, Hawaii, and Japan, but it doesn't occur in Nebraska. So now you can start thinking about what might be offshore and what might be going on there. Now, none of this probably tells you too much about whether this is front-end overload or not, but there's one question here that I want to come back up to you, and one particular sub-question that you need to ask. On question number 1, ask them, does the receiver that's getting the interference have a band pass filter, BPF, a band pass filter on the RF front end? Question mark. You recall that we've drawn any number of times now in the seminar series a design for a good RF front end, which normally has some kind of a band pass filter at the front end, followed by a low noise amplifier, followed finally by any number of mixing and down conversion stages before we finally go into the IF stage of the receiver. And you need to ask if they've got a bandpass filter on the front end. If they've got a bandpass filter on the front end, not to jump too far ahead of the second talk, but if they have a bandpass filter on the front end, then RF front end overload is probably not occurring. But sometimes people try to save money and they try to reduce insertion loss in their receiver design by skipping a bandpass filter and going straight into a low noise amplifier. This is also the case for some systems that have to be frequency hopping, and tunable bandpass filters that track the frequency hopping are more expensive. If they don't have a bandpass filter at the front end, then you may potentially have front end overload occurring. And again, we'll talk about that in a second talk. But if you're ever taking this kind of a questionnaire, ask them about this. They may even say, I don't know what you're talking about, in which case you say, okay, can you give me a block diagram of your receiver system? Can you give me a block diagram that shows this, or can I find it online? Can you give me something? And just work it with the person. And don't make them feel like they're being put on the spot, like you're interrogating them. Make it clear that you're just trying to get enough information to be able to determine whether or not we ought to try to pursue the problem as a potential interference problem. So having made the phone call, we'll assume that we've decided that it looks like there is some kind of actual interference going on. We might even have some clues as to what the source is, and we can now coordinate with the Office of Spectrum Management and with the people who are operating the receiver some set of measurements, presumably or preferably at the location or one of the locations where the interference is occurring. Now, this is one where we're going to want to know how often the interference occurs. If the interference occurs once every 6 months for 5 minutes, we're probably not going to deploy to the site to try to measure the interference, because the chances are we're not going to catch it. But if it turns out that the interference is either continuously occurring or occurs pretty reliably every day, or maybe even every week, or maybe even up to every 2 weeks, then we might be willing to deploy a measurement system to try to catch the interference in the act and decide what to do about it. So this is the stage where we would do the coordination, we would set up travel orders, we would set up the cost accounting center number that would be charged and so forth, and then we would travel to the location where the interference is occurring and proceed with what I called here the measurement phase. There's a lot built into that phase. The purpose at this point is now going to be to find the interference source and identify the interference mechanism. We want to do two things: find the source and identify the interference mechanism. And hopefully at this point we're not going to be looking at half of all interference reports that are not really RF interference. With that said, I can relate one case where we in fact did deploy up to the Pacific Northwest to look for interference that had been reported into a seismic network that was supposed to be part of basically a volcano early warning eruption system for the Cascade Range. And we had a suitcase system, and we went out to sites where the interference had been reported. And these were remote sites, and as we drove further and further and further out into the badlands of eastern Washington state, we said, you know, it's pretty sparsely populated out here. And finally, we got out to one site where they said that they had interference occurring all the time. And we set up and we were making some measurements that afternoon. And as night fell, I saw the Milky Way galaxy brighter than I've ever seen it. No city lights, no lights of any sort, pitch black, no evidence of any human activity anywhere in the area. And the frequency where this was occurring was down in the frequency range around about 170 megahertz. And at that point, my comment was, there is no transmitter anywhere in this area that could be doing this. We went ahead and made some measurements, but we just realized pretty quickly there's no RF interference out here. And in fact, that one turned out to be a case where, to make a long story short, water was getting into some boxes and there was a temperature-dependent effect, and it made the transmitter in the seismic network at these various stations not work properly, and it looked like interference at the receiving end back in Seattle, but we were able to report, guys, there is nothing out here. I mean nothing whatsoever out at these sites. But in fact, what I'm giving away at this point is basically what we would do. And here's how we would do things. We would look first of all at the receiver that's getting the interference, which we'll say maybe has a bandpass filter at the front end, followed by a low noise amplifier, followed by a down conversion stage going into some sort of a detector, and then into some kind of an output like so. And we would look at this system, and we look at its IF stage, and we identify the bandwidth of its IF stage. We need to know that bandwidth. We need to know if it's working in 10 kilohertz, 100 kilohertz, a megahertz. We need to know that bandwidth, because what we will do typically is set up our own measurement system over here with our own antenna, and this will be routed into our measurement system, which has, of course, a set of tunable bandpass filters, a set of tunable yigs, our own mixing and down conversion stages, and finally an IF stage of our own. And all of this is mounted inside our measurement system, which is on wheels, like so. Okay, there's our measurement system on wheels. And what we're trying to do here is replicate with our measurement system what's happening with this receiver. So it's important that this IF bandwidth, if at all possible, be used for our measurements so that we're now seeing the spectrum through the same bandwidth as they're using. We also try to set our detection mode, and we've talked plenty about detection modes in this series. We'll set our detection mode to look the same as their detection mode over here. So again, we'll connect that up like so. So we make our detection mode look like their detection mode, make our bandwidth look like their bandwidth. We're now closely replicating their system. Now suppose that they are operating here on their front end with some kind of high gain antenna, like so, and they're getting interference in with their system operating with some high gain antenna with a really high gain and pretty low side lobes back here. Well, from our standpoint, that's good. Now, what antenna would we want to use? Well, we don't want to use a dish antenna. That's one thing we do not want to replicate. What we want to use over here is an omnidirectional, or as close to omnidirectional as we can get, an omnidirectional antenna. You're probably thinking, well, wait a minute, you just said replicate the bandwidth, right? Replicate the detection mode, right? But use an omni antenna even though they're using a high gain dish? Yes. Because, and this has actually happened, suppose that they're running with an antenna, to take a rather absurd, but still a case that has happened, situation where they have 200 decibels of gain relative to isotropic in the main lobe of that antenna. We're looking for an interference source which allegedly is getting into the system. What are the chances that that interference source is getting into that beam, which is a fraction of a degree wide? Not very high. And in fact, what if they report that the interference typically goes on for minutes or hours at a time? Well, I can pretty much guarantee that nothing is hovering in that beam for more than about a second. Maybe an aircraft at 100 miles distance might fly through that beam momentarily, but nothing's going to hover in that beam other than some helicopter for minutes or hours at a time. So what is their gain in the side lobes back here, where presumably the interference, if there is interference, is actually coming into their system? What's their gain back in there? Do you think it's 0 dBi? Probably less than 0 dBi. It might be, who knows, I'll just pick a wild number here, it might be minus 20 dBi back here in its back lobes and side lobes. That's where the interference is coming in. Now, we're running an omnidirectional antenna. What's our gain over isotropic? Oh, say it's a dipole or some other type. We're about 2 dBi gain all the way around the horizon. So how much more gain do we have on our antenna than theirs on the interference source? Oh, about maybe 22 dB. Now, they might be running a lower gain antenna, so their side lobes might not be so low. Maybe they're only running say a 30 dBi gain antenna, in which case maybe this is, and again I'll pick a number here, minus 3 dBi. Well, again, if we're running 2 dBi gain on our Omni, we've still got 5 dB more gain on our antenna in whatever direction the interference may be occurring than they've got. So we'll see the interference better than they will, we hope. In fact, where they might see the interference kind of coming in and then dropping out and then coming in and dropping out as time goes on, we might get to see the interference a lot more of the time because we'll be seeing the interference all the way down into here and up and down and up, okay? So we try to replicate bandwidth and detection, but we but we'll typically want to use some kind of omni antenna unless we've got an extremely good idea of the direction where we think the interference might be originating. Now, if we know for sure, but for example, before we arrive at the site that correlated the interference to a particular source, obviously we're not going to need to search around, but I'm assuming here that we don't know. We don't know where it's coming from. This scenario, for example, has occurred where a high-gain antenna that was being used for space communications was inside an electronic warfare range, and there was a suspicion, which was not confirmed, that the people who were performing the electronic warfare activities were inadvertently interfering into this communication link because they were turning on electronic warfare systems that they shouldn't be turning on. Well, that's entirely possible. But this is where our survey comes in, because what we'll do is set up this survey and probably run for about 2 weeks. We'll measure, during that time, we'll measure 24 hours per day, every day. We'll go across the band of interest, the frequency range of interest, which presumably is the range where this transmitter, or where this receiver is operating. And we'll continuously, meaning automatically record data. And basically, we'll either run for 2 weeks or until we definitely see the interference occur and we can identify the interference in our data, whichever comes first. And if after 2 weeks we haven't seen anything, and these guys have been reporting interference, and in particular, if these guys can log in time their interference events, and we can correlate their log with our recorded data, we can look to see whether there's anything in our recorded data at these times that could possibly be related to any interference that they're seeing. It's pretty obvious, I think, to state that if they claim that they're seeing interference here and we're logging data continuously and we're not seeing it, and we have a lot more gain out toward the horizon than perhaps they have, we hope. And worst case scenario is these guys are running, by the way, say 2 dBi gain, say they have an omnidirectional antenna, then we're still equal in terms of antenna gain. We shouldn't be any worse, though. And one last thing that I should have mentioned and didn't mention is that we try to get a noise figure in our measurement system which is similar to the noise figure of the so-called victim receiver. Now again, if our noise figure is a little higher than their noise figure, say they're running a very sensitive space communication link, hopefully we more than make up for that with that gain that we have on our antenna that is higher out toward the horizon than their gain. But noise figure is one more thing to look at. We generally, though, can't do much about our noise figure. We get what we get, and hopefully it's low enough to make it work. So basically, if they can log their interference in time or watch for it, if we can watch over here in our data, if we see something happening, then we know that we're actually seeing the source. If we don't see something happening in our data when they say they're getting interference, then whatever is happening to this system is probably not radio interference. We have had this situation occur both ways out on various test ranges. We've had cases where we recorded data for 2 weeks at 4 sites across a test range, never saw any interference even though the system in question that was supposedly getting interference was crashing continually. And on that one, we actually finally went back into their receiver. We actually opened it up. We actually looked into the receiver, and there's a photograph of 2 of our guys, Bill Kissick and Brad Ramsey, actually doing this at a hilltop site in one of our old technical progress reports. And we basically finally established that, in fact, they had a dropout in their data links at this output stage. It turned out that the data was going into a sort of a bit bucket due to a software problem. But we have also had it happen where we not only recorded data while the interference was occurring, but where we were in Florida, where earth stations were getting interference from various airborne sources, and where the earth stations along the Florida coast actually were calling each other on the phone saying, yes, it's happening now. Okay, now it's happening now, now it's happening now. We actually knew it was coming along south down the Florida coast, and we were next. So we actually only had a few minutes to get set up. We got things set up and we ran, and we we got the data on the interfering source right there, and we were set up for a 2-week survey, and we got it in 2 hours. 2 hours after we'd shown up, we had the source. That was lucky, because they had told us that it could be 2 weeks at a time when you wouldn't see any interference. But we were prepared for a long siege, but it turned out that we in fact got the interference almost immediately. But this is the basic approach for this whole stage. In fact, any particular questions at this point in terms of how we try to set up our measurement system at the same location to try to grab or quantify the interference that's going on. Okay, so with that said, I'm going to now get rid of this system here, but I'm going to keep our measurement system in place, like so. And now that we have, let's say, determined that yes, there's RF interference occurring, and yes, we have seen the signal, we got it correlated. This would be similar to what happened, for example, in the case with the earth stations in Florida, where we got the signal, it was coming from an airborne source, and we said, good, and we were able to ascertain from the characteristics of the airborne source what the airborne source was. We then coordinated with the agency that actually controlled that source that was involved in the interference production, and we said, can we come to a particular site where your aircraft are located and measure the spectrum of this source directly? And they said, sure, absolutely, so they let us. Sometimes the interference source may be a fixed source that's close to where the victim receiver is, in which case we only have to drive ourselves maybe a mile, or maybe half a mile, or maybe 1,000 yards to get over. Other times we might have to, as in the case in Florida, drive halfway across the country. But one way or the other, what we'll do next, having identified the source, is now obtain a good spectrum measurement of that system. So this is power versus frequency. And we're going to measure that spectrum. We'll say the spectrum looks like this. Not that all interference is produced by radars, but I've drawn a type of a radar spectrum here. And the goal here is to first of all measure the spectrum with as much dynamic range as we possibly can get, because we may want to have this in our catalog at NTIA for later use for other purposes, but if at all possible, we're going to try to get 100, 110, or even 120 dB of dynamic range. We'll do that by measuring the source itself with our mobile measurement system, now not with an omni antenna, but with, in fact, some kind of high gain antenna, which is directed toward the location where this transmitter is located, over here, okay? And we've talked about how we'd measure radar emissions. We could also do this with land mobile radios in a laboratory environment. We could do this with digital communication links. We could do it with ISM devices. We might measure them outdoors. We might measure them in the lab. Depends on how big the device is and how close we need to get and what our antenna constraints are. But in any event, we're going to try to get a wide dynamic range measurement, which also presumably will cover a lot of spectrum. And in particular, what we've got to get, what we've just got to get, is the spectrum across whatever the band or the frequency or the operating frequency range is of the receiver system that has had or has reported the problem. So if this is the band or the frequency range across which the receiver works, we've got to get the spectrum across that range. The next thing that we do is to measure or note from our data that we've recorded what this power level is. Here's the power at F0, and we measure the power across this frequency range, which may vary or may not vary across that frequency range, but I'm going to write this as power in the receiver band. And we'll assume that these are decibel measurements, so here we get this power level, here we get this power level, and what do we have between the two? We've got the delta. We've got the offset. We've got the offset. We know what the power level of these emissions in this part of the spectrum is relative to the power level in at the fundamental operating frequency. Now, the next piece of the puzzle is to compare This delta, this offset, I didn't draw it well. Let me draw it better. Sorry. Here, I got to come down to here. We'll say it's down there. There we go. There's the delta. There's the power offset between how much power we've got nominally in this part of the spectrum in the bandwidth of that receiver. We've got to measure in the bandwidth of that receiver and, again, in the detection mode of that receiver so that we're looking at that transmitter that seems to be involved in the problem with the same bandwidth and the same detection mode as the radio that has been experiencing the problem. So again, we're going to see these offset levels at the same relative offsets as the receiver would see them. We get this delta, and we'll say for the sake of argument here that this is, we'll say for the sake of argument that it's 65 dB. No particular reason to pick that, but we'll say it is. Now, here I've drawn it as if there's a big frequency offset between these. It could be that we're getting not co-channel, but adjacent channel bleed over. In that case, all we do is measure the communication channel and then just follow it down into the adjacent channel part of the spectrum. But the point is still the same. We're going to see how far down this delta is in this part of its emission spectrum. We'll also note for the record, while we're doing all this, whether or not this receiver meets the emission mask criteria that it's supposed to meet. Here's the emission mask criterion. Emission mask criterion that it's supposed to meet. Now, the way I've drawn this emitter is meeting the emission mask criterion. Just because an emitter meets an emission mask criterion does not mean it won't produce interference. Emission mask criteria have been developed to minimize interference problems. They do not eliminate interference problems. So we'll note whether it does or does not meet the emission mask criterion, because if these emissions are directly causing the receiver's problem, this could bear importantly on the question of who's going to, in effect, pay to get this fixed. If this thing meets the emission mask criterion and it's producing interference, then the people who have the receiver may have to pay to put a filter on the transmitter to get the problem fixed. If, on the other hand, this transmitter is not meeting the emission mask criteria it's supposed to meet, then basically the cost and the trouble of getting and installing a filter on the transmitter may fall on the people who are operating the transmitter, because they're operating outside the mask boundaries where they should be operating. So let's say, as I said, for the sake of argument, that this is 65 dB offset. Well, now we'll come back. I'll continue on this board. We'll come back to the victim transmitter. And if the distance from the victim receiver, if the distance between the victim receiver and the transmitter that we've been measuring is negligible, we can go back and forth between the two like a ping pong ball. If, on the other hand, we're looking at a 2,000-mile drive between them, what I'm about to show you we would actually do while we were originally at the victim receiver site. But here's what we do next, or in any event, do while we're at the victim receiver site. Looking at the victim, and I use the term victim in quotes, we're not trying to make a moral judgment here. It's just it's just terminology, because, as I said, sometimes the problem is actually in the receiver design itself. But we will look at the victim receiver IF stage output. Look at the victim receiver stage IF output. Now, here's its IF stage, like so, which goes from the antenna through the bandpass filter, the low noise amplifier, through some mixing stages and so forth, and then finally through an output. What we'll do is actually come off of some kind of a diagnostic output. Sometimes you've got one provided, sometimes you basically have to disassemble the receiver and make your own output. And we've done that, and we're going to run this into a spectrum analyzer. Like like so. And again, we're going to replicate the bandwidth of the receiver, the detection mode of the receiver, check and check. And having done that, we're going to look on the spectrum analyzer, first of all, at the spectrum analyzer's internal noise, with no input, so we'll terminate this, okay, like so. There's the spectrum analyzer internal noise. Now we'll go ahead and connect it live to the IF output, and with any luck, we'll see this noise level displayed higher than the spectrum analyzer's noise. And what does that mean? That means that we're seeing the IF stage noise, okay, at that point. That's good. In other words, we're seeing their noise level, not our noise level, when we look at this. If we can't see that, then we need to examine whether or not the attenuation at the RF input of the analyzer is actually set to 0. If it's not, we'll bring it down to 0. Hopefully then we'll see it. If that isn't working, and we had to do it, we could always put a little amplifier into the line here. But we want to see their noise on our spectrum analyzer. Then what we do next is look for their desired signal, which presumably we'll see in here looking like this, and maybe we see it across like that, depends on what the system is. We'll see their signal, and we'll wait until that interference occurs at their system, and then all of a sudden, when the interference occurs, who knows what we'll see, but maybe we'll see something that looks like this. Maybe it looks like that, yeah. And in which case we can say, oh, by the way, that's a pulsed emitter. Because remember, we're sweeping this spectrum analyzer in time. We see a bunch of little spikes across there. It's probably not a system that's doing frequency hopping, that's causing an interference. And we can actually kind of connect the dots across on here. And what we're really seeing is the time domain behavior of the pulsed emitter. In any event, we'll draw basically a line across here. And we'll say, okay, there's the power in the receiver at whatever that level is right there. There's the power in the receiver. Okay? Now, the next step is to, and I'll go back over to this board, the first board. So everybody clear on this before I move the board? We're looking at the interference levels superimposed on their desired signals in their receiver. We've got it, and we've got a power level here. And we can back, oh, one more thing I should mention, and we can back this out through their system, including their front-end gain in the IF. We can back this out to a received power level out here in space that's actually coming into their antenna. That's easy enough to do. Okay. Now, we come back to here, and remember that we saw the power that we were measuring in this transmitter relative to the power at center frequency, and we know the distance at which we were located from that transmitter when we made that measurement. So here's the next step. Here's the next step. And so here's what we do next. We do a computation. We look at the transmitted spectrum with its funny little area out here that we measured where the interference was occurring. We know how far we were from this transmitter when we made our measurement. We can correct that to get the power level that should be in this part of the spectrum at any given location away from this transmitter. We also know how much power was up here at its fundamental frequency. So here's power in the unwanted. This is the power in its unwanted emissions down here. Now, we can take either one of these power levels as P sub T, and if we want to, we can incorporate that in decibel terms. This is a decibel equation. Decibels. We'll take PT plus GT. That's the EIRP, right? Effective isotropic radiated power coming out of this thing. We can add to that, because it'll be a negative number, the propagation loss. And this is going to be 27.5 dB minus 20 log of the frequency in megahertz, at which this thing is operating down here, frequency of the receiver, minus 20 log of the distance or the radius r in meters between that transmitter and that receiver. So that's how we get L sub P. And remember that this frequency term has nothing to do with some change in propagation loss as a function of frequency through the atmosphere. This comes from the effective aperture of an isotropic antenna being described as lambda squared over 4 pi times the gain of the antenna in linear terms, and so the lambda squared term becomes a 20 log frequency term when we take lambda as c over the frequency, as the speed of light over the frequency. So this is an artifact of the way that we describe the effective aperture of antennas. So coming back up to here, PT plus GT, that's the EIRP coming out of this thing. We can either do this at F0 or out here at the frequency of the receiver, because we know how much power this thing generates and we know how many dB down we are relatively. We did that measurement. Now we add in the gain of the receiver, and we have to do that in the gain in the direction of the transmitter that we think is causing the problem. So this isn't the gain of the antenna in its desired beam. In all likelihood, this is going to be the gain in one of its side lobes. We might have to do a little antenna pattern measurement, or we maybe can get an antenna pattern, or sometimes you can just estimate, at least somewhat closely. And all of this taken together is going to give you the power that's being picked up at the receiver. And this is where, by the way, having matched the bandwidth of the measurement, to the bandwidth of the receiver is important, because we don't have to do any correction for the amount of power that the receiver is getting relative to the power being put out by the transmitter. If we don't make these bandwidths equal to each other, if we don't use the bandwidth for the measurement equal to the bandwidth of the receiver, then what we would have to do is do a correction, which would be 10 log of the bandwidth of the receiver divided by the bandwidth of the transmitter itself to establish how much power gets into the receiver's IF stage relative to the power in the full bandwidth of the transmitter. But as I say, we don't have to do that calculation, which we would otherwise have to put in right there, if in fact we just do the measurement a smart way. And that's another reason why we do the measurement with a bandwidth that tries to match the bandwidth of that receiver. So now we know how much power should be getting into the receiver, and then we look to see whether or not this is equal to the power that was measured. The power that was measured in the receiver. Are the two equal or not? Or nearly equal? If the two are nearly equal, then we're probably getting co-channel interference. In other words, the whole link budget works itself out beautifully, and we're getting the amount of power in the receiver that we thought we ought to get, and that implies that it's this power directly that's actually causing us a problem in the receiver. If, on the other hand, we do this calculation and we find out that basically we're getting, say, 30 dB more power measured in the receiver, then in fact we can possibly be getting into the receiver from the source, then this is not a co-channel interference problem, because the numbers aren't working out. Now you might ask, how close should we come? Well, I would certainly hope within 10 dB and maybe even within 3, 4, 5, or 6 dB. In other words, we look to see whether the expected power in the receiver, whether that expected power in the receiver equals the actual power being picked up in the receiver to within a few dB. Doesn't have to be an exact match, but we want to see if it's close, if it's possible. In a later talk in this series, in the third talk that I give, I'll give an example where, and this is from Fort Smith, Arkansas, where we basically did this, and these two totally did not match. They were off by like 60 dB. Okay, so it was weird because it looked like co-channel interference, but what we expected to see in the receiver was a level that would have been like 60 dB lower than what we were actually measuring. And since we can't make power come out of nowhere, my first comment was, you know what this means? We're rich beyond our wildest imaginations because we violated the second law of thermodynamics. But in all likelihood, there's some weird interference problem going on, and we're not actually making power or energy out of nothing. So this is the point where, in other words, we can identify, again, whether or not we're getting co-channel interference or whether we're getting some other weird interference problem. So again, having done what I just described, what we look to see here is whether this measured level that we got in the IF is somewhere close within 5 or 6 dB to the power that we would expect to get based on the detailed measurement that we did on the emitter and the link budget calculation that we did from the transmitter through space, through the receiver, to see whether or not we think that this level that's been observed in the receiver is or is not commensurate with what we would have expected to get from the transmitter based on its spectrum. Here's another scenario which would help us separate the possibility of co-channel interference from RF front-end overload. And again, we would do this right at the site. Again, we start off with the IF stage noise running like this, and then we see whatever the desired signal is in the IF, looking maybe, who knows, like that, a couple of digital communication links across like that. And suppose that when the interference occurs, rather than seeing something that comes up across the IF like this, might look like that running across there, okay? Or, as I said a moment ago, it might look like a series of little ticks or hashes running across, which is typically an indication of pulse interference. Suppose instead that when the interference occurs, we don't see any signal in the IF whatsoever, but instead we see this happen. The noise level, which I'll get rid of the spectrum analyzer internal noise down here, because we take it for granted that we are in fact seeing the IF noise. Here we are, we're looking at the IF noise. When the interference occurs, the IF noise actually drops down like this, goes down like that. It might go down by 5, 10, 15 dB or more. The noise drops down like that, and the levels of the desired signals, if we can see them, likewise drop way down or drop out entirely. So we go from seeing a nice healthy system to a system where the noise in the IF drop down and the level of the desired signals drop down. You say, can that happen? The answer is, oh yes. And if that happens, then we have got a textbook case of RF front-end overload. And we'll describe that more in the talk next time, if we see that happen. In other words, you don't see interference occur, but when the receiver's performance drops out and it seems that interference is occurring, inside the receiver you see its noise floor go chook and drop down, and you see the desired signals either drop down or disappear entirely. That's RF front-end overload. And as I say, that's a separate problem. But suppose, to go back to what we're talking about now, suppose that having done everything, we have in fact now ascertained that we're getting interference from a transmitter, and doing all the tests and diagnostics that I've just described, we say, it is co-channel interference, and it is in fact coming from this transmitter's out of band or undesired emissions. So now we come at this point back to the transmitter. Come back to the transmitter. We look at its measured emission spectrum. Maybe it looks like this. Here's frequency. We come across here. We say, Here's the band where the co-channel interference is occurring, and whether or not this meets the emission mask criterion, and here we'll draw it as if it does meet the emission mask criterion, whether or not it does meet the emission mask, draw that a little better, whether or not this does meet the emission mask, and here I've drawn it as if it does not meet the emission mask here. Well, that's irrelevant. The question is, does it meet the emission mask here across the range where the interference occurs? The answer is yes. That would mean, in the case that I've drawn, that although the people who are operating the receiver might need to spend the money for the next step that I'm about to describe, the step itself that nature requires that we take is to somehow filter this emission in such a way that we bring this level down. I'll draw it this way. We have to bring this level down enough to make the interference go away. Well, how much is that? Well, that goes back to the picture I just drew, doesn't it? If in the IF stage we saw the IF noise, and here's the IF stage of the receiver, here's the IF stage of the receiver. Remember that we had the IF noise here. We had the desired signals looking like this in the IF, like so. Now all we need to know is how low relative to the observed level of the interference, which I'll actually draw, I'll draw with this actually, color code it. Here's the level of our interference running across here. We need to know how much that needs to be reduced to get out of trouble. That will depend, this reduction will depends on the characteristics of the receiver. For example, just e.g., we might have to get down to an interference to noise ratio. That's the level of this interference to the noise of the IF receiver. That might have to be less than or equal to, let's say, -6 dB for some types of systems. Or, another alternative, we just have to look at the type of receiver. It depends on the characteristics. Or perhaps we need to get to a carrier. That's the level of the desired signal here, C, the carrier. We might need to get to a carrier to noise level that is, I'm sorry, a carrier to interference, sorry. A carrier to interference. A carrier to interference level, carrier to the level of the interference, I misspoke, carrier to interference, that might be less than or equal to, say, or actually I drew this backward, it has to be greater than or equal to. Carrier is the desired. Carrier to interference ratio greater than or equal to, I'll make up a number, say plus 12 dB. In other words, we need the carrier level of the desired signal to be at least 12 dB or more above the level of the interference. It's just going to depend on, it depends on the receiver. So we look at that. But if we know what the actual level of the interference is in the IF stage of the receiver, and we know what the carrier level is, and we know what the noise level of the IF is, then we can apply whatever criterion we need to use, the I over N or the C to I level, to tell us how much of a delta here, how much of a delta we need to get in the interference to bring it down, and that is the delta that we're going to need over here on the spectrum. So now what we can do on this transmitter is install, just before its antenna, probably at the RF in other words, we'll install some kind of a notch or a band reject filter, notch or a band reject, or band stop, I'll say band reject, band rejection, filter here, where this is the rest of the transmitter circuitry, here. We're going to install a filter after the transmitter, before the antenna, which is going to reduce these emissions by that much across at least that much of the spectrum. So we're going to bring it down to look like that. Bring it down all the way down into here. And then beyond that point, we don't really care what happens. We'll install a filter there that'll bring those levels down like that. Here we go. So we'll draw the reality is it would actually look like this. Hopefully it looks like that. And then it comes back up and the spectrum goes across like that. And that should protect that system. Now, if it's a nationwide problem, we might need to recommend changes made nationwide, but that's going to be the basic idea if we're getting co-channel interference, because there's nothing we can do on the receiver end to mitigate the co-channel interference unless we can move sites away from each other or somehow change the antenna coupling. The only thing realistically, generally, that we can do is to install that right there in front of the antenna, but in order to know how wide that needs to be in frequency and how deep that notch needs to be, we need to have, again, taken the measurements in the IF stage of the receiver so that we know what the interference level is, what the carrier level of the desired signal is, and probably what the noise level of the receiver is, so that we know how much this needs to be reduced, and we can then call a manufacturer on the phone and say, hey, we need a filter that works across this frequency range that has this many dB of rejection. Then we install it and we go to work. And we've had this happen any number of times with radar systems where the radars had spectra that looked like this. We've had it with other systems. It can happen, as Ariel commented, in a land mobile radio system where we have adjacent channel interference. In that case, the problem is to make the roll-off characteristic of the emissions from a transmitter channel even sharper than they were when the interference was occurring. And again, who pays for all this can depend upon whether the transmitter does or does not meet this sort of emission mask. If the thing meets the emission mask, if the transmitter meets the emission mask, then the people who own the receiver might be asked to go ahead and pay for the filter. If the transmitter does not meet the emission mask, then presumably the agency or the entity or the company that owns the transmitter needs to install a filter in order to come into compliance with the emission mask criteria. And again, although emission mask criteria are intended to minimize cases of electromagnetic interference, they don't guarantee that it won't ever occur anywhere. And then I just wanted to check my notes and make sure that I'm not missing anything that I meant to talk about, and the answer is no. So, with that, I conclude the talk and invite any questions or discussion. Any questions from anybody about anything or discussion?